Let us now discuss quantum numbers. The quantum numbers are actually used to locate an electron in atom. To locate an electron in an atom is nothing but, the orbit in which it is present, the suborbit or the sublevel in which it is present, and of course, the orbital in which it is present. To know all these, we require a set of 4 quantum numbers. The first one is principal quantum number. Then azimuthal quantum number. Then, of course, magnetic quantum number. And finally, spin quantum number. Now, these are the 4 quantum numbers required to locate an electron in an atom properly. Let us see in detail about these quantum numbers. Coming to the first one, the principal quantum number. See, it was proposed by Niels Bohr. Discussed this in Bohr's atomic model also. Then, it is denoted by small n. Small n takes up the values 1, 2, 3, 4, and so on. Now, these are, of course, called K, L, M, N shells. When n is equal to 1, it is called K shell. 2, it is called M shell. 3, it is called, 2, it is called L shell. 3, it is called M shell. And 4, it is called N shell. Okay. When n is equal to 1, we call it K shell. When n is equal to 2, we call it L shell. When n is equal to 3, we call it M shell. And when n is equal to 4, we call it N shell. Of course, it can be shown diagrammatically also. Let me just show you. Let this be the nucleus. I've already shown this in Bohr's atomic model. Let me just show it again. Now, this, of course, is the first orbit for which, of course, n is equal to 1. Let me call it K shell. Now, coming to the second orbit. Now, when, of course, this is the second orbit, we call it L shell. Then, if it is third orbit, we call it M shell and final. Okay. Now this is n is equal to 4. We call it N shell. Now, coming to the most important point, principal quantum number gives information about size of the orbit and energy of, you can say energy of orbit, or you can also say energy of electron, because energy of electron is nothing but the energy of orbit in which it is revolving. So simply speaking, it tells us about the size and energy of the orbit. Next, I have three relations to explain, which we will be using while writing the table. Number of sublevels in an orbit can be given as n. If you want the number of sublevels in an orbit, you can just take it as equal to the value of n straight away. Then coming to number of orbitals in an orbit. Orbitals in an orbit can be given by the formula n square. Next, coming to number of electrons in an orbit. I mean, the number of electrons that can be accommodated in an orbit can be given as 2n square. So you have to remember these things. Yes. Now coming to the second one, that is azimuthal quantum number. See, azimuthal quantum number was proposed by Sommerfeld. It's not Sommerfield, Sommerfeld. It is denoted by small l. Now, for a given value of small n, L takes up values 0 to n minus 1. 0 to n minus 1 are the values of L. Suppose if n is equal to 1, the possible L values are, of course, it is a 0 to 1 minus 1, because n value is 1. 1 minus 1 is also 0. So 0 to 0, it is nothing but 0. And when L is equal to 0, we call it S a sublevel. It's called S a sublevel. Similarly, if n is equal to 2, the possible L values are 0 and 1, because it is 0 to 2 minus 1 now. 0 to 2 minus 1 is 1. 0 to 1 is nothing but 0 and 1. Now, as usual, when L is equal to 0, we call it S sublevel. When L is equal to 1, we call it P sublevel. Now, if N is equal to 3, then the possible values are 0, 1, and 2. It is because it is from 0 to 3 minus 1, nothing but 0 to 2. 0 to 2 in the sense 0, 1, and 2. Again, S, P, then D. You can clearly see what I'm writing. In the third orbit, you have 3 sublevels. In the second one, you got 2 sublevels. In the first one, you got just 1 sublevel. This is what I gave in the previous one. Number of sublevels in an orbit is equal to the same n value. Here the value of n is 1 and you got just 1 sublevel. And here the value of n is 2, you got 2 sublevels. Here the value of n is equal to 3 and you got 3 sublevels. Similarly, if we go for n is equal to 4, you'll have 4 sublevels. Let me go for that. N is equal to 4. In that case, the possible values of L are 0 to 4 minus 1, nothing but 0 to 3, nothing but 0, 1, 2, and 3. Now, this is your S sublevel. This, of course, is P sublevel, D sublevel, and this, of course, is F sublevel. See, in n is equal to 4. I mean, in fourth orbit, you got 4 sublevels. That's it. Now let us see the importance of this. Important formula. You know, azimuthal quantum number gives information about shapes of orbitals. Shapes of orbitals. Coming to the shapes of orbitals, let me say that the shape of s orbital is a spherical. You can say spherical with a symmetry or spherically symmetrical. Coming to the shape of p orbital, you know it's called dumbbell. Shape of d orbital is a double dumbbell. And the shape of f orbital can be given as fourfold dumbbell, or simply you can say that it is complicated. So these are the shapes of orbitals about which we can have knowledge from the value of L. Now, let me go for this. You know, the number of orbitals present in a sublevel, because L actually deals with a sublevel. Let me give you the number of orbitals in a sublevel. This can be given as 2L plus 1. This is a formula used. Number of orbitals present in a sublevel can be given by 2 into L plus 1. Similarly, the number of electrons that can be accommodated in a sublevel of course is equal to 2 of 2l plus 1. So these are very important. One last, this is also known as, azimuthal quantum number is also known as orbital quantum number. Angular momentum quantum number. Or of course, subsidiary quantum number. So these are the other names that can be given to azimuthal quantum number. It is also called orbital quantum number because I told you that the angular momentum of electron in an orbital can be calculated using the formula root over L into L plus 1 into H by 2 pi, where you are using the azimuthal quantum number L only. So, because it is used for the calculation of angular momentum of electron in an orbital, we call it angular momentum quantum number. Now, the third quantum number is, it's magnetic quantum number. Magnetic quantum number was proposed by Lande in order to explain Zeeman and Stark effect. What do you mean by Zeeman and Stark effects? Zeeman effect is nothing but splitting of spectral line into fine line. Still simpler lines in magnetic field. This is Zeeman effect. Now coming to Stark effect. Stark effect is again the same. That is splitting of spectral line into fine line, but in electric field. Okay, so that is Stark effect. In order to explain these things, magnetic quantum number was proposed by Lande. It is denoted by small m. For a given L value, the total number of m values can be given as 2l plus 1. This, of course, just now I gave it as the number of orbitals in a sublevel. Of course, as n refers to the number of orbit, L refers to the number of suborbit, m refers to the number of orbital, to the orbital in which the electron is present. So for a given value of L, the total m values can be given as 2l plus 1. And let me also say that the range of M is, of course, minus L via 0 to plus L. In fact, it can also be given as plus L, exactly opposite. Plus L via 0 to minus M. Generally, people follow this. So this is the range of M. We'll discuss about this in detail later. For a given value of L, the total number of M values can be given as 2L plus 1. And the range of M can be given as minus L via 0 to plus L. Now coming to the use of magnetic quantum number. You know, small m gives information about orientation of orbitals in space. What do you mean by orientation of orbitals? I mean, when they are placed in magnetic field, whether they are oriented towards the magnetic field or away from the magnetic field, or they have no deflection at all. Towards, away, with no deflection. Three different varieties. Towards, plus, away, minus, no deflection, 0, like that. That is how you got their values as plus, minus, 0, etc. Let us go for the last one. Coming to the last one, that is spin quantum number. You know, it was proposed by Uhlenbeck and Gaudsmit. Of course, they say differently. People say Gaudsmit or Gaudsmith. Okay, like that. You know, it is denoted by either simply S or MS. You know, S is the spin quantum number, no doubt, but what MS is? You know, we call it magnetic spin quantum number. It is because when, you know, electron is placed in magnetic field, it will have two different spins. Let me show you. You know, just as Earth revolves around the sun and rotates around itself on its own axis, even electron also, while revolving around the nucleus, of course, it also revolves around itself in two different directions. One is a clockwise, and of course, the other one is anti-clockwise. It can even be this also. So, electron rotates around itself in two opposite directions. One is clockwise, the other one is anti-clockwise. You know, the clockwise spin has the ms value of plus half. You know, the value of S is only half, but only when it is placed in magnetic field, it will have two opposite orientation. Clockwise, for which ms is given as plus half, and anti-clockwise, for which ms is given as minus half. In general, the clockwise spin is represented as this or this. A full headed arrow mark pointing upwards or even half-headed arrow mark pointing upwards is okay. In case of anti-clockwise, you can show it this way or this way. So this is what spin quantum number says us. Let me tell you that spin quantum number gives information about spin of electron around itself on its axis. So this is very important. Spin of electron around itself. Spin of electron around itself on its axis. Okay. Now let me draw a table with so many things like what the number of orbit is, number of orbit, and of course the designation given. Designation of the orbit. Next. The total number of total number of sublevel. See, when I say number of orbit, it is of course n. Coming to total number of sublevels in an orbit, the formula is n only. Next. What are the different values of L that we have? Plus what is the designation given? Then coming to the total number of orbitals. In a sublevel, I've already given the formula. In a sublevel, it is 2L plus 1. If I take the total number of orbitals in an orbit, even this was given, formula is n square. I'll show you all these. Just give me time. Coming to the range of M. Then the total number of electrons in a sublevel. When I say total number of electrons in a sublevel, the formula is total number of electrons in a sublevel is it can be given as 2 of 2L plus 1. I've given this formula. And finally, the total number of electrons in an orbit. Now this can be given as 2n square. That's it. So this is a very big table that I am going to give. Okay. Okay. Now let me start with the first orbit. The number of orbit, of course, is 1, and the designation given to this orbit is Cation. First orbit is also called Cation. And the total number of sublevels that can be accommodated in the first orbit is nothing but n, nothing but only 1 again, because the value of n is 1. Now coming to the values of L possible, we know that the values of L possible for a given value of n, even this can be written as 0 to n minus 1. I've just given. So here it is only 0. And the designation given to that sublevel is S. Coming to the total number of orbitals in a sublevel, this is the value of L. And now I have to use the formula 2L plus 1. 2 into 0 plus 1. So the total number of orbitals in S sublevel is only 1. Only 1. This is the number of sublevels. And see, in sublevel also it is 1. Overall in the orbit also it is 1 only, because we have just one sublevel. So even the total is also the same. And here, this is the orbital for which the range of M is, I told you that it is, of course, I go with plus L via 0 to minus L. This is the order. Plus L. What is the value of L here? 0. So I can write it as a plus a 0, 0, minus a 0, whatever it may be. It is only 0. Now the number of electrons that can be accommodated in this sublevel, we know that it is only 2. So let me write this as 2 electrons. Now even in the total orbit also, only 2 can be accommodated. You can check out the formula. In this case, it is 2 of 2 into 0 plus 1. So 2 of 2 into 0 is 0 plus 1 is 1. 2 into 1 and you got 2. And if you want the total number of electrons in an orbit also, it will be 2n square. The value of n is 1. So 2 into 1 square is 2. So this is how you can actually give all the things in a proper way. So this is for the first orbit. Let me go for the second orbit. The designation given to second orbit is L shell. L, the number of sublevels. Of course, number of sublevels is equal to the value of n. So let me write 2. But what are they? 0 and 1, because it is 0 to n minus 1. Now when L is equal to 0, we call it S sublevel. And now when L is equal to 1, we call it P sublevel. These are the designations given to the two sublevels, S and P. Now consider these L values. 2 into 0 plus 1 is 1. Only one orbital in S sublevel. 2 into the value of L for P is 1. So 2 into 1 plus 1 is 3. This is the number of sublevels. This is the number of orbitals in the sublevels. In S you have 1 orbital, in P you have 3 orbitals. Overall, I can say that it is 4. That is the total number of orbitals in the whole orbit. Orbit has 4. But when you say S a sublevel, it has only 1. Let me show you this way also. Coming to this S, of course, is this. S will have, S sublevel will have only one orbital. For that, as the value of L can be seen, it is 0. So plus L, I told you that I take from plus L to 0, plus L to minus L via 0. So the value of M is what I'm writing here. This is the value of M. Of course, it is 0. And now when you go for 3 p orbitals, let me start with plus 1, 0, minus 1. Most of the people, of course, give it as minus 1, 0, plus 1, but that is wrong. It's actually plus 1, 0, minus 1. Okay. Next, coming to the number of electrons that can be accommodated in this is 2. And here it is, of course, a total of 6. Both put together, it is 8. So the total number of electrons that can be accommodated in the second orbit is 8. In S sublevel is 2. In P sublevel is 6. So that is how you have to check it. Now let me go for the third orbit. See, the third orbit is, of course, called M shell. Now the total number of sublevels. Of course, we know that the total number of sublevels is only the value of n. So let me write the same 3 again. Coming to the values of L, 0 to n minus 1. So it has to be 0, 1, and 2. When it is a 0, we call it S sublevel. When it is 1, we call it P sublevel. When it is 2, we call it D sublevel. And come on, when it is 0, 2 into 0 plus 1 is 1. When it is 1, 2 into 1 plus 1, it is 3. When it is 2, it is 2 into 2 plus 1, it is nothing but 5. So overall, if you take the total, it is 1 plus 3 plus 5, 9. You can use this n square formula. See, 3 square is equal to 9. That's how you got everything. So just check with that. 9. Next, coming to the range of M, I have to be little clear. In S, of course, we have only one box, one orbital for which the value of M is, of course, from this you can write. It is clearly mentioned here. Plus L, nothing but 0. 0 minus L is minus 0, nothing but 0. That's what I've written. Coming to when L is equal to 1, look at what I'm going to write. So this is plus 1, this is 0, this is minus 1. This is when L is equal to 1. When L is equal to 2, of course, it will be 1, 2, 3, 4. Let me take 1 here. So overall, it is plus 2, plus 1, 0, minus 1, minus 2. Okay, the total number of electrons that can be accommodated. See, in S you have only one orbital, in P you have 3 orbitals, in D you got 5 orbitals, a total of 9 in the whole orbit. Now come on, let us fill up the electrons. In this, of course, 2 electrons. In this it is 6 electrons. And here, of course, it is a total of 10 electrons. Now, overall, the orbit can actually accommodate a maximum of 18 electrons. You can just check that out. 2 of 2L plus 1 can be seen from this. Suppose if you take 0, 2 of 2 into 0 plus 1, 2 of 1, nothing but 2. If you take it as 1, 2 of 2 into 1 plus 1, nothing but 2 of 3, nothing but 6. 2 of 2 into 2 plus 1, nothing but 2 of 5, that is of course 10. This way, we can write the total number of electrons that can be accommodated in a sublevel as well as in an orbit. Now, when the orbit is fourth, we call it n shell. Now, because the value of n is 4, even you will have 4 sublevels. 0, 1, 2, then 3. When it is a 0, we call it S. When it is 1, we call it P. When it is 2, we call it a D. And when it is 3, we call it F. So that is about the designations of the sublevels. Now come on, 2 of L plus 1. I mean the total number of orbitals. 2 of 0 plus 1, 2 of 1 plus 1, 2 of 2 plus 1, 2 of 3 plus 1. Okay, coming to the total number of orbitals, let me say 1 plus 3 plus 5 plus 7. That is 4 plus 5, 9. 9 plus 7, it's 16. You can just use this formula n square. N square is 4 square, right? 4 square is 16. Now come on, let us write the range of M carefully. Now in S sublevel, you got just one orbital for which the value of M is 0. I've already given. In case of P, of course, it is plus 1, 0, minus 1. 3 orbitals. Now in case of D, you have 5 sublevels. I think you got 1, 2, 4, 5. Yes. For this, it is plus 2, plus 1, 0, minus 1, and this is minus 2. Finally, for F sublevel, you got 7. Let me just take this whole area. 1. This is anyway the second, third, fourth, fifth, sixth, and seventh. Consider the black one also. Now this will be plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. This is what you have to consider. Yes. Okay. Now let us fill up the electrons in them. In the first one, of course, we can fill up 2 electrons. 1, 2, 3, 4, 5, 6. In P sublevel, you can fill up 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10. You can fill up a total of 10 electrons in this. Now look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and this is 14. So you can fill up a total of 14 electrons. 2, 6, 10, and here it is 14. So overall, it is 2 plus 6 plus 10 plus 14. That comes out to be 32. Total of these 4 is 32. So you can fill up 32 electrons in fourth orbit. Yes,